Hi, if you're watching this video, you're watching the last lesson in the optics unit. In this lesson, we'll be talking about the wave model of light. We'll be talking about how scientists discovered whether or not light acts like a particle, like atoms do, or like a wave, like sound waves. This has been a debate for years and years and years, right? Some scientists thought that light should be a particle, like atoms, and that they fly out like that, like little pieces. Many scientists also thought that light moves like a wave, like sound wave does, with ups and downs. And so scientists would go back and forth because they'd be like, well, light acts like this, so it must be a particle. But then other scientists would say, well, light acts like this, so it must be a wave. And so for years, people have thought, the scientists have been split on this idea. Isaac Newton was the first one to hypothesize that light was a particle. This theory explained why light traveled in straight lines, right? This is why we draw ray diagrams using straight lines, because light travels in straight lines. And it also explained how light reflected and how light refracted. Light reflected because the particles of light would bounce off. Light refracted because the speed of the particles changed. But one thing it didn't explain was how light could be made of different colors. And so scientists also hypothesized that light could also travel in waves, like sound. And this was called the wave model of light. This explained why light could be split into different colors. So when we look at this, we see that this wave is how light travels. And this is what light is. This explained how light could be shown in different colors. So to understand the wave model of light, you need to understand a few key terms. You need to understand crest, trough, wavelength, amplitude, and frequency. These are 5 terms you need to know to understand the wave model of light. A crest is just the highest point of a wave. So if you're looking for the highest point of a wave, you're looking for the crest, right? The highest point of the wave. The trough is the lowest point of the wave. The lowest point of the wave. When we talk about wavelength, we're talking about the distance between 2 crests or 2 waves, not one or the other, right? Not crest to trough, it's crest to crest, high to high, or low to low. A common mistake you'll make is if I ask you for the wavelength, you would say this to this, but that's not the wavelength. This is crest to crest. Or trough to trough. Basically, when does the wave repeat itself? That's the wavelength, right? So this is the highest point of the wave. It goes down and up. It goes back to the highest point again. That's the wavelength. We start at the lowest point. We go up then down, back to the lowest point. That's the wavelength, the distance between the lowest to the lowest or the highest to the highest. Amplitude is the height from the center. So we would say the height of the wave is this, all the way from crest to trough. But amplitude is from the middle to the height. From the middle to the height. That's the amplitude. Frequency is how many times a second a wave repeats itself. So when we talk about frequency, let's say this distance, it took the wave 1 second to travel this distance, or the particle or wave to travel this distance. Okay, well, for this wave to travel this distance in 1 second, it only made 2 crests, right? So it only repeated itself 2 times here. Here it repeated itself 1, 2, 3 times. Here it repeated itself 1, 2, 3, 4, 5, 6, 7 times. So the number of times it repeats itself in a second is called its frequency. And we measure frequency in hertz. So this repeated itself 2 times, so 2 hertz. 3 times, 3 hertz. 7 times, 7 hertz. That's it. Frequency is how many times the wave repeats itself in a second. So the frequency of a light wave is also how we see color. Different colors are actually just different frequencies, right? So when we see red light, we're actually seeing the lowest frequency of visible light. It's the slowest light. It is the light that repeats itself the lowest amount. Orange is a little bit higher, yellow gets higher, green, blue, indigo, and violet is the highest frequency. It repeats itself way more times than red does in 1 second. So red is the lowest frequency. Red is the lowest frequency, while violet is the highest frequency. Red is the slowest, has the lowest amount of energy, and repeats itself the lowest amount of time, so it has a low frequency. Violet light has the highest energy, the most frequency, and repeats itself the most. So it has a high frequency, right? That's the difference between the colors of light. That's really the only difference. They're made up of the same thing. It's just one is moving faster or vibrating or moving up and down faster than the other. Why is light a wave? Why is that important to know? Well, the wave model also explains some of the odd properties of light. For example, light can interfere with itself, right? These dark bands here, these shadows here, are because light is blocking itself. If they were particles, they wouldn't do that because they would travel in straight lines like that. So when we look at an experiment where we cut 2 slits into paper and we shine a light through it, we would expect to see, if light was a particle, 2 lines because, well, this is where light can travel through, right? Light is traveling through here. It gets blocked by everything but these 2 little slits. Well, that must mean we only see 2 little slits. And you can do this experiment at home to prove it, right? If light was a particle, we would see this, but what we actually see is this. We see these series of bands. And so this proves that light can travel as a wave. Because if it traveled as a particle, well, the particles get blocked here and here and go through and make this band of particles of light. And so you would see 2 bands. But because we see a series of bands, we can say that light is interfering in these dark spots. They're blocking themselves. The light waves are blocking themselves. As well as there are bright spots, which means light is also making themselves stronger in certain sections. We call this interaction interference. As waves of light interact with each other, they can increase their amplitude. They can increase their amplitude or cancel out each other's frequency. This creates the bars of light we see. Constructive interference, as you can see, these 2 bands of light, these 2 waves of light, made a bigger wave of light. And so you can see these bright bands. The destructive waves, or destructive interference, these waves of light basically knocked each other out. And so no light was produced. And so you see these dark bands. Constructive interference. If 2 waves meet at the same point in their wave, like crest to crest or trough to trough, the wave becomes larger, right? So if we look at this, trough to trough, crest to crest, they're matching up, right? They match up. So because they match up, right, the crest becomes larger, the trough becomes longer. And so instead of something like this, you end up with something more dramatic. And so this is called constructive interference because they're constructing a bigger wave. Destructive interference is when waves meet each other at opposite ends, crest to trough, right? This is the trough, this is the crest. Crest, trough, crest, trough, crest, trough. And so this high point gets knocked out by this low point. And so they cancel out and you end up with destructive interference because it's destroying the wave. And so you end up with this scenario. As light is passing through the 2 slits, right? So we have the light source, wave, 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 wave. Now waves are being produced here and here, and they're interacting in different spots, right? They're interacting in different spots. And so you create these bands of light because where they're interacting destructively, they're canceling out, creating dark spots. And where they're acting constructively, they're creating these light spots. So as light waves pass through the two slits, the waves interact with each other. Some cancel out, others don't. So this video will talk about that in detail. And if you want to do this experiment at home, it's actually very easy. You just take a dark, very opaque piece of paper, hopefully a thick one so it blocks more light. Cut 2 slits into the paper. Take a bright flashlight and shine it at a wall in a dark room. The waves of light will travel through the slits, interact with each other, and create that banding pattern you see. And it's a famous experiment that helped prove that light can travel as a wave. Hopefully you found this useful, and I'll see you next lesson.